Sometimes it is necessary to work with measurements that are way smaller or much larger than the standard unit. In such cases, we use units related to the standard unit in multiples or submultiples of 10. Okay, so we have here submultiples, alright, of 10. We have the first one to be deci, we have centi, we have milli, micro, nano. Deci is 10 raised to the power minus 1, centi is 10 raised to the power minus 2, milli 10 raised to the power minus 3, micro 10 raised to the power minus 6, nano 10 raised to the power minus 9. We have multiples, deca, hecto, kilo, mega, giga, tera. 10 raised to the power 1 for deca, hecto 10 raised to the power 2, kilo 10 raised to the power 3, mega 10 raised to the power 6, giga 10 raised to the power 9, tera 10 raised to the power 12. And these are their symbols. Okay, DC, small letter DCM for deci, centi, milli. We have the micro sign, the mu sign representing the micro. We have small letter N for nano. We have DA for deca, H for hecto, K for kilo, small letter K for kilo, big letter M, G, T for mega, giga, tera, respectively. Okay, so what are these prefixes and how do we use them? Let's say you're measuring a length and the length you're measuring is way smaller than the meter. So let's say we measured a length and it's 0.1 meters. Okay, using the meter scale. But of course, we want to make it more relatable by bringing in one of these prefixes to make the number more friendly. Alright, so let's try to work with the deci. So how do we change this to decimeter? Okay, now we know that deci is 10 raised to the power minus 1. So if we want to bring in deci into this place, it means we are trying to factor in 0.1. So since deci is 0.1, let's multiply and divide this digit by 0.1. okay, so we multiply the whole stuff by 0.1 divided by 0.1. You agree with me that the numerator 0.1 and the denominator 0.1 cancels out to be 1. So this is 0.1 meters times 1, which will give us 0.1 meters, just the way it is now. Okay, so if we take out the top 0.1 and exchange it or replace it with the D for deci. Okay, of course you know deci is 0.1, so this is the same thing. So we'll be left with 0.1. So what we do now is we now take this remaining one and put it into the equation. We take it to alter this other number here, the 0.1 on the right side. So what we then have will be 0.1 meters, alright, divided by 0.1. Of course, multiplied by D. Okay, so we can have this to be our answer, but then this goes into this other numerator here. So we're going to have, of course, 0.1 decimeter divided by 0.1. But then if we solve this out, of course, this is the same thing as saying 0.1, okay, times 10 raised to the power 1, or times 10. Then we have decimeter. Okay, so the same as doing this. This 0.1, this is 10 raised to the power minus 1. Okay, 0.1. So we move it up, it becomes 10 raised to the power 1. So this is what we have, 0.1 times 10. Of course, this is 1 decimeter. Let me just go over it briefly. We needed to convert 0.1 meter to decimeter, right? So basically what we did was introduce decimeter into the number we have by bringing in 0.1 divided by 0.1. Okay, now we took one of the 0.1 to represent deci. We replaced it with the small letter D, okay, which is a symbol for deci. Then use the remaining value, the remaining 0.1, to alter the number that we had previously and then multiply it by the deci. So this is how we have 1 decimeter. So let's try another one. Let's try this time with the 100 grams. Okay, so let's say we have 1,000 grams and we need to convert that to kilogram. So what do we do? Of course, kilo is 10 raised to the power 3. We can see that from here. It's 10 raised to the power 3. Okay, so what we need to do now is to multiply this number we want to change by 10 raised to the power 3 divided by 10 raised to the power 3. Of course, it's like us multiplying it by 1. Okay, but then it's going to help us get to alter it the way we need to. So we have multiplied by 10 raised to the power 3, that's 1000, divided by 10 raised to the power 3. Okay, so that's 1000 divided by 1000. Okay, so we want to bring in kilo into this. So what we need to do, of course, we take that 10 raised to the power 3 numerator out, replace it with the k. Of course, we now use this other denominator value to alter the number. So of course, what we're going to be having now will be 1000 grams divided by 10 raised to the power 3, which is also 1000. Let me erase that briefly. Okay, so which is also 1000 multiplied by k. Okay, so of course we know that this 1000 here, we take out this 1000 here, the zeros would go at each other. So what we're going to be left with is 1, of course, k, 1 kilogram. Okay, of course, k times gram will give us kilogram. So we have 1 kilogram. So this is how we get to put measured values in very relatable forms. Okay, we make use of the submultiples and multiples. You can see here we had 1000 grams. It looks like a number that you might not be able to relate with properly if you don't know, even if you know the gram scale very well. Okay, but then 1 kilogram is more relatable. All right, let's do one more. Okay, so let's say we have a cup of water and we've measured it, and what we got is 0.7 liters. Okay, but we want to make it more relatable, you know, by bringing in submultiple. So what do we do? Okay, so let's say let's bring in the milli. Okay, so let's bring in the milli to have milliliters. So what do we do? Since the milli is 10 raised to the power minus 3, that's 0.001, we multiply this number we have by 10 raised to the power minus 3 and divide by same thing. All right, so we have this divided by 10 raised to the power minus 3. Okay, all right, so of course we can take out the top one to bring in our milli. Okay, we have milli now. All right, then we take this other one into this equation, the 10 raised to the power minus 3 denominator, into that other number, and what do we have? This is 0.7 liters times 10 raised to the power 3. Of course, the negative has to give way because it has been moved upwards. Okay, and all this now is multiplying the milli outside there. So of course this is going to be 700 milliliters. Okay, so we have 700 milliliters. All right, so you can see we can use this multiple or submultiples for any quantity. Okay, that we want to measure, and we just use them to give our measurements better representation. Okay, so it's good enough you practice with them and get used to them. When you get used to them, you won't have to do all these calculations to just get an answer. You can just look at it and know. Of course, you can just look at 0.1 meters and know it is 1 decimeter. Okay, because of course if you divide this by 0.1 or you multiply it by 10, it's 1 decimeter. Okay, you can look at 1000 grams and know that, oh, this is 1 kilogram. Of course, because if you divide 1000 by 1000, you have 1. Okay, you can look at 0.7 liters and know this is 700 milliliters. Because if you, of course, multiply this by 10 raised to power 3, or you divide this by 10 raised to power minus 3, which is the milli, you're going to have 700 milliliters. Do you get? So with time, with practice, you're going to get used to just looking at them and knowing what the answer will be if you try to impute any of the prefixes. So let's consider dimensional analysis. Any quantity measured in the unit of any of the fundamental units has the dimension of that fundamental unit that measures it. So let's take, for example, length. We have to know that dimensions are represented with their symbols enclosed in square brackets. So we have length, and length is represented by a capital letter L enclosed in square brackets. Next we have mass. Mass is represented with capital letter M enclosed in square brackets. We have time, same thing. We have Kelvin, same. We have ampere, which is capital letter I enclosed in square brackets. We have candela, which is small letter CD enclosed in square brackets. We have amount of substance, which is mole, enclosed in square brackets. So dimension analysis has applications, and we're considering 2 of them in this course, and they are to find dimensions of new physical quantity. So it means we can use dimension analysis to find the dimensions of new physical quantities. Then we can also use them to check for the correctness of physical equations. So let's get to actually try these applications right now. So first of all, we're finding dimensions of physical quantities. So first of all, let's find the dimensions for volume. Okay, so we know volume is length times breadth times height, okay, which are all 3 representations of length. So we can say length times length times length, okay, in other words. And so this can be represented with capital letter L enclosed in square brackets, and this will automatically give us capital letter L enclosed in square brackets raised to power 3. Alright, now this is the dimension of the physical quantity volume. Okay, so let's move to speed. Speed is distance over time. So we know that distance is a representation of length. So what we're going to have here is L, capital letter L enclosed in square bracket divided by capital letter T enclosed in square brackets, which gives us LT raised to power minus 1 enclosed in square brackets. This is the dimension for speed. Okay, remember we're finding dimensions for physical quantities as the first application of dimensional analysis. So here we have next acceleration, which is change in velocity over time. So we have change in velocity as LT raised to power minus 1, okay, divided by capital letter T enclosed in square brackets. Remember that acceleration is change in velocity over time, and we have found speed, which is same as velocity, okay, apart from the difference of direction, okay, but of course they both have same formula. So change in velocity is LT raised to power minus 1, remember all in capital letters and enclosed in square brackets. We divide that by capital letter T enclosed in square brackets, and we have LT raised to power minus 2. Okay, so we do same for force. Force is mass times acceleration, and mass is capital letter M enclosed in square brackets, and we've just found acceleration. So if we combine all this, we have MLT raised to power minus 2. Okay, we're supposed to have this as multiplication, not division, please. Okay, so this is mass times acceleration, so that gives us MLT raised to power minus 2. Alright, next let's use this to check the correctness of equations. So let's try to check the correctness of area of a circle. Okay, so we know the area of a circle is pi r squared. Now pi is a dimensionless constant, but we have radius, which is a representation of length. So radius is going to be represented by capital letter L enclosed in square brackets. Okay, so we can see that the equation we have is correct, because actually the dimension for area is L enclosed in square brackets raised to power 2. Okay, so we just confirmed that from this, because remember, arrow is a representation of length, so this is capital letter L enclosed in square brackets because of the arrow, while this pi is a dimensionless constant, so it's just numbers. Okay, it doesn't have a unit, it's just numbers, it's dimensionless, so we don't add any dimension for it. Alright, so let's move on to the next. We have the next as velocity. So we have u equal to at as one of the equations of velocity. Okay, so u represents velocity here, a represents acceleration, t represents time, and then we have their dimensions written just beside them. Of course, we know that velocity is lt raised to power minus 1, acceleration is lt raised to power minus 2, and time is capital letter T. Alright, so we move to confirm if what we got in the previous slide, where we looked for the dimension of speed and we got lt raised to power minus 1, we are checking if it's accurate. So we're going to be confirming that with this other formula, which is even different from the distance per time which we used. Okay, so therefore we have lt raised to power minus 1 here equal to lt raised to power minus 2 in square brackets, of course, times capital letter T in square brackets, which comes from this T here, and this lt raised to power minus 2 comes from A, which is the acceleration. So this is acceleration times time, T. Alright, so if we join that together, if we simplify this equation, we have lt raised to power minus 2 plus 1. Okay, if we do simplify this further, of course, minus 2 plus 1 is equal to minus 1. So we can see that this equation is actually correct for velocity. Let's move on to one more. Let's confirm for distance. Okay, using this equation, s equal to ut plus half at squared. Now, s represents distance, which is capital letter L, u represents velocity, a represents acceleration, t represents time. And we have all the dimensions here. We have L for s, L to raised to power minus 1 for velocity, L to raised to power minus 2 for acceleration, and t for time. So if we replace this equation with the dimensions, we have this. Okay, simplifying this, we have lt, okay, we have lt raised to power minus 1 times t. If we simplify that, we're going to have lt raised to power minus 1 plus 1. Okay, because from indices, of course, we know this is what we should get. Then we have lt raised to power minus 2 plus 2. Okay, simplifying this other side of the equation. Okay, so simplifying this further, we have minus 1 plus 1, okay, equals 0. Anything raised to power 0 is 1. So we have 1 times L. Minus 2 plus 2 is 0. Anything raised to power 0 is 1. So we have 1 times L, which gives us L plus L. Now, note that this equation is correct, because if we simplify this further, we're going to have capital letter L in square brackets equal to 2 times capital letter L in square brackets. Now, that 2 is a dimensionless constant and is of no consequence when we're discussing dimensions. So once we have all terms of the equation equal, then we have a correct answer. Alright, so this is correct.